Hey everybody, this is part C2 of the sinusoidal functions unit. It is the final lesson in the unit, and we're going to talk once again about regression, but this time talking about it in terms of sinusoidal functions. So just like we did with all of the other ones, quadratic, cubic, exponential, logarithmic, we're going to do the same thing for sinusoidal regression. This is our general equation here, so y equals a sine, and then brackets bx plus c plus d. Just a reminder, d is our midline point, and a is our amplitude. Okay, and then one final piece of information that we can get from this is that the period is equal to 2 pi divided by our b value. All right, so these are some pieces of information that we can get just from the equation. We're going to take a look at a couple of word problems, come up with the equations, and see if we can figure out some information about these situations. So example number 1 says, we have this data here from the U.S. Naval Observatory in Washington, D.C., which shows the altitude of the moon in Vancouver on October 25th, 1999, so well before any of you were ever born. So what we're going to do is we're going to take this table of values, we're going to plot it on our graph, we're going to find the line of best fit using Desmos, then we got a couple of questions at the bottom. Okay, so one important thing to note on this graph is that my x values, each line is counting up by 1. And my y values, each line is counting up by 5. So we got 0, 5, 10, 15, 20, and so on. Okay, so that's just something important to note when we plot the data. So at 0, we're at 48.6. So at 0, we're at 45. So between 45 and 50, somewhere right there. At 1, we are at 48. So almost level. At 2 o'clock, we're at 44. So we're a little bit lower than that, just below the 45. And we're going to keep plotting these points until we get, well, we'll see what kind of shape it is, but it should have a sinusoidal shape. So I'm going to pause the video here. I'm going to let you put the points on your graph as well, and then we'll jump back into Desmos. So it's a little hard to see, but I do have my points all written down here, and I have my points all going up here as well. But we are asking two questions on here. So we're asking for what is the sinusoidal regression function, which we're going to do together in a minute. And then we're going to take a look at when is the moon unable to be seen. Now, logically, if you think about it just in a regular day, when do you not see the moon? You don't see it during the day. So we're going to take a look at how we can interpret that question as well. So what I'm going to do is I'm going to flip over to Desmos. I've already made the table of values. Hopefully you have already done that as well. I'm also going to talk about how we can readjust the window so we can see the points. Because right now on my graph, I can only see 2 of the points. So if we look at our x values, our lowest x value is 0. Our highest x value is 23. And then for my y values, they seem to go up to about 48-ish, and they go as low as negative 8.6. So when you click on the wrench icon, I'm just going to change what we can see in terms of the x-axis and the y-axis. So because my lowest x point is 0, I'm going to maybe change it to, I don't know, negative 5 or something like that, and make it go up to 30. For my y values, again, we're going into those negatives. So maybe let's go as low as, I don't know, negative 20, and let's go as high as 50. So now we have a better idea. We can see our points here. We can see the shape. They go down, and then we don't have any data after that. And then they start coming up again at 17, and they go back up. Okay, so when you are readjusting your window, think about what range of x values am I looking at based on the data, and what range of y values. Just kind of keep that in mind. Now we're going to look for the sinusoidal regression equation, so we're going to click this little branch leaf looking thing. We get that, and we're going to change in the drop-down menu to sinusoidal regression, and we get a graph that looks like that. Again, make sure that you write all of your a, b, c, and d values to 2 decimal places. So I'm going to write it down here, y equals 39.40 sine bracket 0.24 x plus 1.64 close bracket plus 10.28. All right, and I'm going to flip back to the notes so you can write that down as well. So make sure, again, you round your numbers to at least 2 decimal places, but you won't lose marks if you write the whole thing. So better to be safe than sorry. I mean, just write down the whole thing. It takes an extra 5 or 10 seconds. It's not going to hurt you in the end. Now, part B says, over what time period is the moon unable to be seen? And the way that we can interpret that is when the altitude of the moon is below 0, that's when we can't see the moon anymore. So what we're going to do is we're going to click on our 2 x-intercept points, and we're going to just write down the times of them, and that's when my graph is below 0. So that's when the moon cannot be seen. All right, so just flipping back here. So I've got my equation written down here. Over what time period is the moon unable to be seen? I really should have written down the numbers before I switched back. That's okay. So it is 7.25 to 17.96. And then we're just going to talk about how do we interpret that. So 7.25 does not mean 7:25, like 7 whatever, like if you're thinking of the time 7:25. What this means is it is a quarter of an hour after 7. So 7.25 is technically 7:15 because there are 60 minutes in an hour, so a quarter of an hour is 15 minutes. 17.96, again, there's no such thing. There's no time as 1796 because our minutes and stuff only go up to 60. So we can interpret this as 17, I don't know, like 58, something like that. So this is the time range that we are looking at. So again, don't just give the answer that Desmos tells you, but give it some context as well. Example number 2 says, in 2011, the Singapore Flyer was the largest Ferris wheel in the world. We have a table here that gives the height of a rider from the ground at different times. So when they started keeping track of the time, it was at 49 feet. And then after 9.25 minutes, it was at 295, blah, blah, blah. You can see the rest of the data here. So we mentioned in the first lesson that whenever we have something that is circular, like a wheel or something that goes back and forth, that is going to be a sinusoidal function. Okay, so anything that is circular can be modeled by a sinusoidal function. So we're going to enter this table into Desmos, get our equation. Maybe we'll even draw a graph of it just so that we can visualize it. And then we'll get into what the question is actually asking. So I have all of my data on Desmos, so I'm going to switch over to there. And again, we're going to just talk quickly about how do we adjust the window. So again, in our settings, we can see that our x values start at 0 and they go up to 75. So I'm going to adjust my window to kind of account for that. So let's go from -5 to 80. And then my y values go as low as 49 and as high as 541. So maybe we should make our y-axis go from 0 to, I don't know, 600. So we get something that looks like this. There's all of our points that are plotted. Let's go ahead and make a graph of it. So again, we click on the leaf, switch it to sinusoidal regression, and we get this equation here that goes up and down, so on and so forth. Now, what the question is actually asking you says Jordy got on the Ferris wheel at noon and rode it for 4 consecutive rotations. His friend Yale was in a building directly across the street at a height of 400 feet. When was Jordy level with Yale? So basically the question is saying, when was Jordy at 400 feet? So on our graph here, we have 400 feet here. But the other key part of the information says that they wrote it for 4 consecutive times. So if we started here at 49 and we went up to the top and then we came back down to the bottom. So that's just one time going around. Went up, and came back down. So that's 2 times. So we're going to have to adjust our window even more, and maybe we'll have to double our x-axis, because right now we can only see 2 of the 4 rotations. So instead of 80, I'm going to double that amount to 160. And now we can see up, down, up, down, up, down, up, down. We've got the 4 rotations there, and the last one is at 148 and at a height of 49. Okay. Now, again, that's not what the question is asking. The question is asking, when is he at a height of 400 feet? So what I'm going to do is I'm going to make another line. I'm going to enter y equals 400, and we're going to write down all of the intersection points. Okay, so the first one, where y is equal to 400, we get x is equal to 11.85. The second one is at 25.15, 48.85, 62.15. By the way, how is it weird, or is it just me, that this person is riding a Ferris wheel 4 times, and he's on this ride for like hours and hours and hours? Maybe it's just me. I don't know. I'm not a big Ferris wheel person. All right, and the last one is at 136.15. Okay, so I'm going to switch back one more time to the notes here and just show my work here. So I entered y equals 400, and we got all of these x values where y is equal to 400. But again, just like in the last question, we don't just want to give the x values, we want to give context to it. So it says that he started riding the Ferris wheel at noon. Okay, so noon is 12 p.m. So this is 12 o'clock. My pen is dying here. So we're starting at 12 o'clock, and my time is in minutes. So the first time he hit 400 feet was 11.85 minutes after 12 o'clock. So we could write that as 12:11. This one is 12:25. This one is 12:48. Now this one is 62, so it's not going to be 12:62. It's going to be 1:02 p.m. 85 minutes is 1:25. 99 minutes is 1:39. 1:22, again, we've gone up another hour, so that's 2:02. And 1:36 is 2:16. So again, we're not just looking for the x values, we are also looking for what the x values are in this context. All right, so the big takeaway from this is, again, just make sure you know how to do sinusoidal regression, know how to enter a table of values and find the correct function, but then also know how to interpret the information. How do you plug in an x value? How do you plug in a y value? How do you know if you're plugging in an x or a y value? All of these things are going to be really important for the test, for the exam as well. But other than that, we're pretty much doing the same thing that we've been doing for all of the other regression.